My name is Siva Balakrishnan, and I'm a assistant professor in stats here. So I'm a colleague of Ryan's. He just gave me a deck of slides and said, teach this. So if you have questions, I'll just say, ask Ryan. But I'm only half joking. But OK, so let's quickly just recap some of the things you talked about last time, and then we'll start some new things. So in the last class, you were talking generally about convex problems. So there's some general structure for convex problems, which is you're minimizing some convex function with convex inequality constraints and affine equality constraints. So that's some general structure that these problems have. They have some nice properties that make them somehow useful and attractive in practice. One of them is that local minima for convex problems are all global minima. So there are no bad local minima in some sense. The other fact is that even when the solution is not unique, the group of solutions forms a convex set. So if you take convex combinations of minima, you obtain back some minima. Perhaps the most important thing, in my opinion, that you guys covered was this first order optimality condition. So what it says is that a point x star is optimal for a convex program. So you're thinking of a program of the form minimize some function f of x subject to x being in some set C. And you want to say, here's an x star. I want to know if this thing is optimal or not. There's a first order certificate of it. So if f is differentiable, then it must be the case that the gradient points, the negative gradient points away from every point in the set. So pictorially, what's going on, you have some convex set, and you want to say some point x star is optimal, then it must be the case that if I look at the negative gradient, it must point somehow outside from the set. Right? So this is the negative gradient at this point x star. It has to somehow push you out of the set if x star is to be optimal. And if an interior point happens to be optimal, then this is equivalent to the condition that the gradient is 0. Right? So if x star happens to be in the interior, then that condition, so the first order optimality condition is the same thing that you should be familiar with. It's just saying that the gradient of f at x star should be 0. Right? So, or if there are no constraints equivalently, then you have this condition. Okay? Is everybody okay with that one? Yeah, so this is a gradient of a function. What's the question?
So you give an example of convex set in our function.
So I want to minimize a convex function with x belonging to some convex set. So the gradient is the gradient of the objective function. It's a vector in this same space that x lives in. And so if you think about it pictorially, the gradient is some vector like that. You're taking some point y here, and you're saying this angle should be obtuse. Right? So I'm not taking the gradient of any set. I'm taking the gradient of the objective at some point in the set. Any other questions? OK, so the other thing that you covered was this idea that you could rewrite convex problems in various different ways and obtain other convex problems that in some cases are easier to solve. So you can eliminate equality constraints in some cases. You can eliminate inequality constraints. You can partially optimize out variables, and you'll end up with a different convex optimization problem. So you have a convex optimization problem. You can try to analytically optimize out some of the variables, and this will give you a new convex optimization problem. Right. So today we'll pick up at where Ryan was at the end of his last class. We'll talk about this idea of relaxations, and then we'll look at two relaxations that happen to be tight. Right? So what is the idea of relaxations? So you're trying to solve some problem, which is you want to minimize some function over x in some convex set C. Or let's think about some case where this maybe is not convex, or it's convex and has a very complicated description. Then you can try to say, I'm going to relax this. I'm going to instead solve a problem, which is you minimize this function over x in some convex set, hopefully convex set C twiddle, where C twiddle is bigger than C. So I've enlarged the feasible space. And so one thing that I know is that whatever function value I obtain, it'll be a lower bound on the function value for this problem because I've enlarged the feasible set. So this is just a way of taking a problem potentially non-convex or convex and difficult and trying to reduce it to relax it to a simpler problem, which you can then try to solve. And it turns out there are some cases when such relaxations are tight. So that is, even though you're solving this relaxed problem, you'll obtain a solution which will be correct for the original problem that you cared about. And we'll see some examples of this. Oh, by the way, Ryan said you don't have to write notes. Like everything's in your slides. It says I'm old-fashioned, so. All right. Okay, so one example of this is where you're trying to relax what are called non-affine inequalities. So the setup here is you're minimizing a convex function, but instead of having just convex inequalities, you have some, and affine equalities, you have some convex equalities. So I have things that say gi of x should be equal to 0. These are some constraints that I have. And so think of, you have some D or P constraints like that. Right? And then maybe you have the usual set of other equalities and some inequalities and so on. Right. So the new thing or the twist is that you just have some convex functions that are now equal to 0. These are constraints. You can check that this is no longer a convex problem. Right? So this is a non-convex problem. It's because these are not necessarily affine, so they're convex. And so the set where a convex function is 0 is not necessarily a convex set. But you can relax it, and the natural way to relax it is to just relax all these equalities to inequalities. So you just write down this problem where I say you minimize f, subject to these gi's being less than or equal to 0, and the usual things. Right, so this is a relaxation now. There are more feasible points in that second case. And in general, this relaxation will not be tight, but we'll just look at one example where it is. But is everybody okay with the idea? So convex equality is not a convex set. Convex inequality is a convex set. This thing? I don't know where I can move it, though. Okay, so maybe I can avoid using the center, if that will help. No? Okay. So let's look at an example of this. So this is a problem from Boyd and Vandenberg. Thank you. Now I feel worse about not doing that, but all right. Okay, so here's the setup. It's a maximizing your utility kind of problem. So it's an investment problem of some sort. So I have some initial amount that I can spend, x0, and I'm going to try to spend, well, actually maybe I should call this, okay. So I have some initial budget b0. I'm going to try to spend at each time some amount x1 through xt. So these are the things I'm trying to optimize. I have some utility function u, which is an increasing concave function, which is just how much money do I get or how much utility do I get for spending some X dollars, right? So you have additionally some constants alpha 0, alpha 1. I'll tell you what they are, but they're roughly telling you how important each day is, and each alpha is positive. And the way that this budget works is that at every day I invest it. So I invest B0, and I get back some function of B0. So this is some return on my investment. And then I spend some amount of it. So I spend, say, X0. And this is how much I'll have at the next time step. And this function, which is my return on investment, F. So this is my return on investment. And this function is also increasing and concave. Okay, so what's the goal? I just want to maximize something, which is I want to maximize the sum of alpha I times xi. Right, so these are the scalars, times the utility at xi, subject to constraints, which are, say that at every day I can only spend a positive amount. So xi's are all positive. And b at time t plus 1 is equal to b at time t plus my return on that investment minus how much I decide to spend. Okay, so this is the problem. Right? So at every day, I invest some money, I get some return, and then I spend some money. And for spending that amount of money, I get some utility back, and I want to maximize my utility. Okay, so what's the problem here? It's not a convex program. So I'm maximizing a concave function, that's fine. The problem is that this constraint is not convex. So the natural thing to do, it's not convex for precisely that reason. So the natural thing to do is to try to relax this. And so I can say, suppose that at time t plus 1, I just say I have at most this amount. Right? So this is now a relaxation of this problem. What's the intuitive explanation for what I'm doing? I'm saying that I can spend this amount. I actually have exactly this, but I can throw away some money. Right? So now you're seeing why maybe this relaxation is tight. Right? So maybe at optimum, and this is now easy to argue, you can argue that at optimum you won't throw away any money, so all of these constraints will be tight at optimum. Right? So the utilities and the investment returns are all concave and increasing, so more is better. So you can conclude that at optimum, so this is a relaxation, you can solve this relaxation, and now you can argue that the optimal solution will satisfy all these constraints with equality. You will never throw away any money.
Is that a requirement for relaxation to be tight?
Is that all the equality constraints are met at optimum?
Yeah, so ideally, I mean, the way to say that is, yeah, if you solve the relaxation and you end up with a solution that's feasible in the original problem, then your relaxation is tight. Right? Not anything fancy. But, any other questions? Okay, so this is just an example here. You can relax it to inequality constraints, solve the problem, and you'll end up with a solution that satisfies the constraints of the original problem. Okay. Wow. Okay, so what's the next example? The next example is something called principal components analysis. I'm lazy. All right, so what is the problem of principal components analysis? So the version that's in your notes is it's called SVD, I guess. So you're given some fixed matrix X. Say it's in Rn cross T. And you want to find a low rank approximation to this matrix. So what does that mean? I want to find a matrix R that is closest to X in the Frobenius norm sense. So I'm minimizing over R. And the constraint that I have is that the rank of R should be exactly K. Okay, so this is called the problem of low rank approximation. I'm taking some matrix X. You should think of K as smaller than N and D. But I want another matrix R, which has small rank, but is close to the original matrix in Frobenius norm. You can think about trying to do this. So Frobenius norm is just the entry-wise sum. Right, so if you did this to the covariance matrix, then so SVD of a covariance matrix is often called principal components analysis, but this is just an SVD problem. Right, so this is a non-convex problem. Why is this non-convex? Perfect, right? So the objective is convex. The rank is not a convex thing. So how do you see this? I mean, there are many ways. You can take any matrix and say, I don't know, half A plus half minus A, I guess is 0. So I can take convex combinations and get much smaller rank. I can also take convex combinations and get much larger rank. So if I take matrices that look like that, right, I'll end up with a matrix. I can take a convex combination of two matrices that have rank 1 and end up with a matrix that has rank 2. Right? So there's some sense in which the rank is not a convex function. Okay, but it turns out that this is one of the most important non-convex problems that we know the solution to somehow. Right? So the solution is just given by the singular value decomposition. So the optimal R here is just UK some diagonal UK transpose. Right? So where this is just the singular value decomposition truncated to K entries. Right? So this is the truncated SVD of X. Right? So the optimal R, whatever R star, we know what it is. Even though this is a non-convex problem, there's some sense in which you can actually say what the optimal solution is, and you can compute it efficiently. What we'll do now is we'll try to write down a relaxation and try to argue that that relaxation is often tight, so that you can view this as you can obtain the solution by solving a relaxation instead of doing some sort of Gaussian elimination or whatever you would do to compute an SVD power method. Is everybody okay with this? Okay, so what's the relaxation? So the first thing is that you need to observe that you can instead minimize. So the original problem of PCA is equivalent to minimizing over Z's, where Z is now going to be a projection matrix. And rank of Z is K. And I'm going to minimize X minus X times Z Frobenius norm squared. So you should think of at optimum, Z will just be equal to VK, VK transpose. Right? So the optimum Z here is just VK, VK transpose. So this is a projection matrix, and it will optimize this objective. Right? So it's equivalent. If you knew Z, you could figure out V, and from V you can figure out the other two factors. Right? So this is just a different way of posing this PCA problem. It's just saying find me the best way to project the original matrix X into a rank K dimensional subspace so that I preserve as much of the Frobenius norm as I can. Is everybody okay with this? Good. Right, so this is still a non-convex problem. I've only made it worse, if anything. Right, so you can now say, okay, what is the set that I'm really optimizing over? So there are two things. One of them is, okay, So you can expand out the square, right? This is equivalent to minimizing which in turn is equivalent to maximizing the trace of x transpose x times z. So the objectives you can just rewrite. So use the fact that ZZ transpose or right, so a projection matrix is idempotent. So expand out that square and you'll end up with this equivalent. So minimizing this over z is equivalent to maximizing this over z. If you don't see it, just expand out the square and believe me for now. What's the constraints? Right, so the constraints that you have is that Z should be a symmetric matrix. You can say, what is a projection matrix? A projection matrix is one that has eigenvalues which are all either 0 or 1. So and we still have this fact that the rank of Z is K. Okay, so this is the set that I want to optimize over. So I'm just rewriting what all those things I wrote in words, I'm just writing them out in math. Okay, so now since all the eigenvalues are either 0 or 1, the rank of Z being equal to K is the same as the trace of Z being equal to K. Right, so this is, since every lambda is either 0 or 1, the sum of the eigenvalues is the same as the number of non-zero eigenvalues. So these two things are the same. And so what have we done so far? You can, we're still at a non-convex problem, but you can say it's equivalent to maximizing the trace of x transpose x times Z, subject to Z being in the set where it has trace, Z is K, Z is symmetric, and lambda I of Z, so the eigenvalues are all either 0 or 1. Okay, so the last step of this relaxation, so we're just building towards a convex relaxation. So the only thing that's left that's not convex is this fact that I require the eigenvalues to be either 0 or 1. The convex relaxation of this constraint is to say that every eigenvalue is between 0 and 1. And so I drop this integer constraint, replace it with this constraint, and now this is a genuine convex relaxation of the original thing. Right, so if you want, this is just saying that in the PSD ordering, Z should be trapped between the zero matrix and the identity matrix. Yeah?
Constraints on the eigenvalues of Z?
So I'm just defining for you what a projection matrix is. So a projection matrix is an idempotent matrix, but that means that every eigenvalue of it has to be either 0 or 1. That's the definition of what it means to be a projection. It's an orthonormal matrix. Any other questions? Yeah. Symmetric matrices. So, I don't know. Z is equal to Z transpose or whatever. It's a bunch of linear constraints on Z. Yeah.
All the eigenvalues or just the
All of them. So I wanted originally all of them to be either 0 or 1. Now I want all of them to be between 0 and 1.
If the largest one is between 0 and 1, then all of them.
So you need that. So this is implied by something, right? So if they're all positive and the largest one is less than 1, it implies what you're saying. But yeah. Yeah.
You mentioned that having all the eigenvalues 0 or 1 makes it a normal matrix, but I thought that all of them have to be 1 to be an orthonormal matrix.
So it's a rank deficient orthonormal matrix, right? Like so I want it to be a low rank projection, so I don't want it to be a full rank orthonormal matrix. So it's just, yeah. Any other questions? Okay, so so this constraint set is it's called the Fantope. And we've defined something. It's a relaxation of the original SVD problem. It says rather than solve this non-convex SVD problem, you can think of maximizing the trace of z times. So this is some linear objective with some convex constraints. So that is z belongs to the Fantope. And the main point is, okay, so some things turn out to be true. If it so happens to be the case that the original SVD problem has a unique solution, then this relaxation will be tight. That is, it will be achieved at exactly the rank k projection of the original matrix, the rank k SVD. So z at optimal will be exactly equal to vk transpose if vk was unique. Right, so in any non-degenerate problem, the Fantope relaxation is not a relaxation. It's a tight thing that if you optimize this, and it's precisely for the same reason as in that case, you will never pick an eigenvalue that's strictly between 0 and 1. You'll either choose to use that direction fully or not at all. Right? So at optimum, it'll turn out that all the lambda i's will either be 0 or 1, and exactly k of them will be 1, at least provided the original problem has a unique solution. Okay, so why did we do all of this? One reason is that this perspective makes it easy to think about regularizing. So if you wanted to solve a problem like sparse PCA, then it's much easier to start from here than to start from some non-convex problem. Right? So if you start from the non-convex problem, you can add a regularizer, but then you don't know what it's doing. The way that people derive, so what is sparse PCA? I want to solve the same problem, but I want that these V's that I get out of the SVD should somehow have many zeros. Right? So that is, I want a sparse solution. So the way that people come up with, think of the traditional sparse PCA problem actually turns out to be you solve this maximization of trace of x transpose x times z. Z is now in the Fantope with some parameter k. And I'm going to regularize it by adding something like lambda times the L1 norm of z. So this turns out to be, well, this. Right? So this turns out to be an interesting relaxation of sparse PCA. So somehow relaxing it to a convex problem gives you some insight in how you might think about regularizing the problem. And at least in the unconstrained case, it turns out that the relaxation is tight. Okay, any questions about this? All right, so you've seen two examples where relaxations of convex problems or non-convex problems turn out to be tight. Right, so now we're shifting gears. We're going to talk about canonical problem types. So let me just give you some high-level overview of what we'll see. So Ryan gave me like 40 slides, and at this rate, I'll cover like 10 of them. But hopefully that's his problem. But I don't know how he covers this material this quickly. But all right, so okay, canonical problem types. Okay, so there's some sense in which you can think of convex problems as being some big set. There are special cases that we can often solve quicker than general convex programs. And so as a result, we've sort of divided convex programs into a bunch of classes which are increasingly more general. These are these nested classes. And the intuition is that some of them are easy to solve and they get increasingly more difficult to solve. So we'll try to prove something. It's in this picture that Ryan has. So there's some class of problems called linear programs. So this is where the objective and the constraints are all linear. These are embedded in a class of quadratic programs. So quadratic programs are ones where the objective is quadratic, but the constraints are all linear. Convex quadratic. And then you can think about an even much bigger class that nests both LPs and QPs. These are called semi-definite programs. And then these are all actually special cases of something called conic programs. And all of these are special cases of convex programs, which are special cases of non-convex programs, right? So there's a reason for trying to think about this type of hierarchy. One of them is that, in general, you should think about it as if your problem's an LP or a QP, it's very likely that an off-the-shelf solver will solve a pretty large instance of the problem. So these are, in some sense, very easy to solve. SDPs are much, much harder to solve. So a generic SDP, unless it has a lot of structure, you will not easily be able to solve it for more than, say, 500 variables, unless there's a lot of structure. And then conic programs are just much, much harder than even SDPs to solve. Right? So in some sense, you should think of LPs and QPs. These are the things that you'll see most in like machine learning applications and so on. And that's because they're somehow very easy to solve. So SVMs, lasso, basis pursuit, everything that you can think of will be special cases of these little bubbles inside. There are things that are SDPs. So the Fantope thing is an SDP. But probably you will not be able to solve that program for very large instances. Right? Is everybody okay with this? So we'll just try to now define what all these problem types are. We'll see a few examples, and then we'll try to prove that this hierarchy works like this. That is, LPs are a subset of QPs and so on. Okay, so first, what are linear programs? The general form we think of for a, so in all of these, there are things called standard forms and general forms and inequality forms and so on. So there's historical reasons for these names, but they're all equivalent forms. So what is the general form of an LP? So you're just trying to minimize some cost vector that's fixed, C transpose X, subject to a bunch of equality and inequality constraints. Right, so some constraints of these forms. This is called a linear program. It has a linear objective, linear equality constraints, linear inequality constraints. So everything is linear. So the way maybe pictorially to think about it is if you slice out these constraints, then what you're left with is this. These inequality constraints define something called a polytope. Right? So each of these constraints will say you have to be on this side of, on some side of some plane. And you should imagine sort of slicing up like that. And so the feasible region, the region that satisfies that constraint, will be some polytope. It's the intersection of a bunch of half spaces. And now, what are you trying to do? There's some vector, cost vector C, and you're trying to go as far in the negative direction, say, as you can. Right? So in this case, I don't know, maybe I should have pointed it towards something. So in this case, maybe you're asking how far down can I go without leaving this feasible set, and it'll turn out that the optimal will be somewhere here. Right? So there's some cost vector that you should imagine, and you're trying to go in the opposite direction. Is everybody okay with what an LP is? So the feasible set is some polytope. The cost vector tells you in what direction you want to go. And it'll turn out that, and maybe Ryan will prove this eventually, but the optimum will often be at a vertex of this polytope. Okay, so what is the standard form of an LP? So the standard form just eliminates all the inequality constraints except for component-wise inequality constraints. So you say you're trying to minimize C transpose X subject to some equality constraints and some trivial, sort of simple inequality constraints. Right, so you no longer have constraints that look like this. They all have to be of the form x is bigger than 0. This is for some reason called the standard form of an LP. Okay? These two are equivalent. The way to go from one to the other is to introduce a bunch of slack variables. So you introduce some variables that say Cx plus S is equal to D. And then you minimize over these guys as well. Right, so you've seen this in the last lecture, but maybe the high-level point is there's a standard form over there and a general form over here, and they're equivalent. You can reduce from one to the other by introducing some slack variables. Okay. Is everybody okay with this? Good. So let's look at some examples. Okay, so before we do, I'll just say, okay, so LPs are extremely important in practice. They are used for a lot of planning and operations research problems. So for example, Tepper here teaches an entire course on linear programs. It's fairly important as a topic, and there's a lot of work that has gone into designing solvers for these things and so on. They're just important sub-problems. Kantorovich, who introduced linear programs to the world, also won the Nobel Prize for it in economics. Right, so they're just important things. All right, so let's see some simple examples of linear programs. Okay, so the first one is something called the diet problem. Ryan has a note saying it's especially important for graduate students. I don't know what that means, but it's just a simple problem. Okay, so there's some cost per item. So there are D possible things you could eat. Per unit, there's some cost C1 through CD. There's some given things which are how much of Dij says how much does nutrient let me say this amount of some nutrient I in the food item J. And there's some minimum nutrient intake. So Di is the minimum amount of nutrient I that you'd like to consume. And basically you'd like to minimize your cost subject to some constraints, right? So what are the constraints? So I'm going to say X is the amount of food item that I choose to consume. Right, so my objective, the thing I'm trying to minimize, which is my cost, is just C transpose X. So I'm consuming amount X of food item I or whatever. And then my constraints are that the nutrients that I eat or consume have to be at least this vector of D. And presumably I have to consume positive amounts of everything. So this is the so-called diet problem. It's just saying, how do I minimize my cost subject to some constraint that I have to consume at least some amount of nutrients? I didn't come up with this. All right. Okay, so what? Okay, so let's do a slightly more interesting example. So this is something called basis pursuit. So the setup here is you'd like to solve a system of linear equations, but they're underdetermined. So you're given some matrix X. It's in n times P. And P is much bigger than n. And I'm given some vector y in Rn. And I'd like to solve this linear system that y is equal to x times beta. But because, so this is a problem of so-called high dimensional statistics. So this matrix X has very few constraints. So it's n is much less than p. So it's a fat matrix like that. So this is an underdetermined system in general. So that is, there are many betas that will solve this system. Right? So there are many solutions. And to make the problem sort of well posed, you're going to try to find one particular solution that has some structure that maybe you like. Right? So one thing that maybe you would ask for is that you'd like to find the sparsest solution. So what does that mean? I'd like to find the solution beta that minimizes the L0 norm subject to y is equal to x times beta. Okay, so this is potentially one thing that I could want to solve. The L0 norm is just the number of non-zero entries. Right? So it's the sum of the indicator that beta j is not equal to 0. And it's just counting how many non-zero entries are there. So the way to think about this, you have some system of equations. There are many possible solutions. You'd like to pick one, and maybe you'd like to pick one that's sparse. That is, it uses the fewest number of these variables in its representation somehow. Okay. This is also a non-convex problem. It's non-convex for a very similar reason to why the rank is non-convex. The objective here, so the L0 norm is not convex. It's not convex for the same reason that the rank is not convex. Right? So I can take two vectors that have one non-zero each, combine them, and get a vector that has two non-zeros. Right? So the L0 norm is not convex. So again, we'll go back to this idea of relaxations. So one way to relax the L0 norm thing is to construct its convex hull. Turns out that in this case, that's the same as minimizing the L1 norm. So you could say, instead of minimizing the L0 norm, I'm going to minimize the sum of the absolute values of the betas. And this problem is known as basis pursuit. So this is called basis pursuit. And one way of motivating it is as the convex relaxation of finding the sparsest solution to a system of equations. The other way is you just think about it as I'm trying to find a solution that has a small L1 norm. Okay, so I want the solution that has the smallest L1 norm. This is a convex function. This is easy to check. So this triangle inequality tells you this is convex. It's a convex. And so you could potentially solve this problem. The claim is that this is an LP. This is actually a linear program, even though it doesn't look like it. So how do we see that this is an LP? So one way is to try to introduce some proxies for the absolute value. Right? So let's suppose I wanted some new variables zi's that I want them to behave like the absolute value of the beta i's. So I'm going to say that zi should be at least beta I, and zi should be at least negative beta I. So this, and now I'm just going to say the same thing. Y should be equal to x times beta, and I want to minimize the sum of the zi's. And now I'm minimizing over both beta and z. Right, so this is a relaxation in some way, right? Like, so I could end up at a solution where z is much bigger than beta, so z is bigger than the absolute value. But you can convince yourself quickly, since you're minimizing over z, you will pick z to be exactly the absolute value of beta. That's the minimum z that satisfies both of these constraints. And you have the original set of constraints. Right, so this is just equivalent to this problem here. So you can write down this thing, and this is obviously an LP. There's a linear cost and a bunch of linear constraints. There's some linear equalities and some linear inequalities. So this is just an LP. Any questions about this one? Okay. So the next one is trying to ask this question. So it's called the Danzig Selector. So it's a estimator in this similar setting. It's for doing high dimensional linear regression. So you should think about the problem where you have noise now. So y is not exactly equal to x times beta. There's some noise in your measurements. So maybe you don't want to exactly force these equality constraints. You want to force some other version of it that allows you to have some noise. And this is one way of doing this is the lasso that you've seen before. Another way of doing it is via this thing called the Danzig Selector, which is an LP. So what's the way to do this? So let me just write out what this estimator is. You're going to say minimize the L1 norm of beta subject to some weird looking constraint. What is that constraint? It says x transpose y minus x beta in L infinity norm should be at most lambda. And so lambda is some tuning parameter. Okay, so this program, whatever it is, it's called the Danzig Selector. I'll try to motivate it in a second. But for now, the first thing to observe is that this is also a linear program. You can convert it to a program that looks like that in exactly the same way. The L infinity norm being less than lambda is the same as each entry of this vector being less than lambda. Those are all linear constraints. The L1 norm you can relax in the same way. So this is an LP. And now one can ask, okay, where did this thing come from? Okay, so one way to motivate it is to think about unconstrained least squares. Okay, let me just so in unconstrained least squares, so least squares is a way of doing regression. Again, it's trying to fit x beta to some y's, but you want to, instead of fitting them exactly like in basis pursuit, you want to minimize the L2 discrepancy, right? So linear regression is the problem of minimizing the L2 norm of y minus x beta squared. Okay, so this is unconstrained least squares. You've seen this before, hopefully. The solution to this you can find, since it's an unconstrained problem, I can take the derivative. So suppose I'm in a low dimensional setting, I can take the derivative and set it to 0. The derivative here is just x transpose times y minus x beta. I would set it to 0. And this will tell you what the solution to the least squares problem is, which is just it's x transpose x inverse x transpose y. So this is just, you can solve unconstrained least squares. But if you stare at this, this is exactly this thing that in unconstrained least squares, we said the gradient has to be 0. Here, we're trying to say, okay, the gradient can be non-zero, but I'd like it to have a small L1 norm. So I'm trying to trade off this gradient quantity with this L1 norm quantity. So I'd be very happy if you found me a solution where this thing is small, but also the L1 norm is small. And that's the intuition behind what this Danzig selector is doing. If you prefer, if you think like a statistician, then this is just saying every column of x, so every predictor has a small correlation with the residual. Right? That's what the constraint is forcing. If any column had a large correlation with the residual, then you should include more of that column in your regressor. Right? So you should stop including things in your regressor when none of your columns, none of your variables are predictive of the residual. That's what the Danzig selector is trying to do. Any questions about this one? Yeah. Yeah, so, I mean, okay, so there's the optimization way of comparing is lasso is a QP, whereas this is a linear program. So there's some sense in which they're different. In terms of statistical facts about these two things, they're identical, essentially. Right? So everything that's known about Danzig is known about the lasso. historically, what happened was that the high-dimensional statistics revolution started off by a paper that Immanuel Candes and Terence Tao wrote about this thing. So it's a precursor to theorems about the lasso. Even though the lasso is a much older estimator, people didn't know how to prove things about it until they saw how you could prove things about this one. So in some sense, everything that's true about the lasso is true about this. It's a different estimator, but very mildly different in practice. Any other questions? Okay. All right, so next thing that we're going to talk about is QPs. Do you usually take a break in this class at some point? Do you want to take a break now? Yeah, take a break. Let's continue. So we're just going to talk about quadratic programs now. So a convex quadratic program is one where the objective is quadratic. So the objective looks like some linear thing plus some quadratic thing. So there's an x transpose qx. And you have the usual linear constraints. So quadratic objective with linear constraints is called a quadratic program. A QP will be convex if you can try the second derivative condition, right? So take the second derivative of the objective, and require that this matrix Q has to be PSD. Right? So it has to be symmetric and all its eigenvalues have to be positive. Right? So these are called convex QPs. So whenever this Q matrix is PSD, these are called convex QPs. Okay, so it's clear that they generalize LPs. Right? I just set Q to be 0, and I'll get back an LP. We'll try to situate them in that hierarchy later on, but for now, they're just something bigger than linear programs. Turns out that these are also things that you can solve fairly quickly. Let's look at some examples. So you've seen one somewhere there. Least squares is an example of a convex quadratic program. So the way you see convexity is you look at the Hessian. The Hessian here will be x transpose x, which is always a positive semi-definite matrix. So the least squares objective is a convex quadratic program. The other one that you've seen, I guess, is the lasso. Right? So that's another case where, again, so the lasso is just say subject to some L1 constraint. You can turn this using that same trick that we used before into a bunch of linear constraints. So this will in fact be a quadratic objective, convex quadratic objective with a bunch of linear constraints. So the lasso is an example of a convex QP. The other one that's common that you've seen again in your last lecture is SVMs. And so I guess in hinge form, an SVM is you minimize over beta. This thing plus some hinge loss term. Right, so over all the examples, you minimize something that looks like this. This is the, I guess, hinge loss form of support vector machines. Again, you can check. You can rewrite it in the Slack form, and then you'll see that these are just a bunch of linear inequality constraints. And this is the quadratic piece here, the half of the norm of beta squared. It's convex because its Hessian is just the identity. So if you take the second derivative of the norm with respect to beta, you'll get back the identity. So it's a PSD matrix. So this is also an example of a convex quadratic program. Is everybody okay with these two? Okay. We'll look at a different one. This is a economics-ish example. So this is something called Markovitz's portfolio optimization. So here the idea is you want to invest in some stocks and they have a stochastic return. So it has some mean and some variance and covariance that you know. Right? So there is some mean return for investing some amount in some stock, but the stocks might also have some correlation. So if some stocks go up, maybe others will go up, and some go down, some might go down, and vice versa, and all of these things, right? So there's some matrix sigma and some vector mu. So this is somehow the mean return for each stock, and this is some covariance between the returns. And you'd like to design a portfolio that has high mean return but has low volatility, that is, it has low variance. Right? So you would like something that maximizes mu transpose x. So x is your investment. Let's say you can not short sell again. So x's are all positive. The sum of the x's is some budget b. Right. And you want to maximize your mean return, but you don't want the volatility to be too high. So you want to solve some program that looks like this. Right, so you'd like a low variance, high mean solution, investment portfolio. Right, and again, this is an example of a convex quadratic program. Covariance matrices are always PSD. So again, you negate this objective, then the second derivative, the Hessian, is just sigma, and sigma is PSD. Okay, is everybody okay with the example? Right, so this idea comes up a lot. This idea of trading off mean investment for mean for variance. You'd like low variance, high mean. You can try to trade those off in some way. Often you'll end up with a QP like that. Okay. So the next thing we'll talk about is semi-definite programs. So you guys have seen cones before, yes? Okay, so then that's good. All right. Okay, so there's again a standard form and a general form for SDPs. So in this case, it's actually non-trivial to see that they're equivalent, but let's start off with the standard form. So the way to think about the standard form of a semi-definite program is you're optimizing over some matrix variable, and you're thinking of something like an LP, except it's over a matrix valued variable. So you want to say something like there's some matrix X. You should think of it as symmetric, and we'd like to solve something that looks like an LP. Like, so it's minimize some cost. I have to define some notion of a dot product with this matrix X. So you should think of this as C transpose X, subject to a bunch of equality constraints. Say and instead of just assuming that X is entry-wise positive, if you assumed X is entry-wise positive, then you'd get back an LP. What you assume here is that X, the matrix variable that you're optimizing over, is PSD. Okay, so this is called a semi-definite program. The idea is you should think of it like exactly like an LP, except the matrix that you're optimizing over, instead of being entry-wise positive, is positive semi-definite. I haven't yet told you what those dots mean. Right, so what is C dot X? So what is the usual dot product? If I think of U transpose V, it's just the sum of UI VI. I can think of generalizing this dot product to matrices. That's just going to be the sum over ij of Cij times Xij. So you can think of stringing these two matrices out as big vectors and taking their inner product. Right? So that's this. It's also equal to the trace of C transpose X. So sometimes this inner product is called the trace inner product. And so you can now plug these things in there. So it's just saying take the trace of C transpose X and take the trace of AI transpose X equals PI. Right? So all of these are just, this is a linear function of the matrix X. This is a linear function of the matrix X. So you have some linear equality constraints, a linear objective on the matrix X. The only thing that's different from an LP is you have semi-definite constraints. That is, the matrix that you're optimizing has to be PSD. Okay. So you've seen one example of a SDP, which is that Fantope thing there. You had some constraint that said that matrix Z, that projection matrix had to be PSD and less than the identity. Right? So there were some semi-definite constraints in that Fantope optimization thing. Let's look at a different one. This one's called matrix completion or trace norm minimization. So what's the setup here? It's kind of like basis pursuit, except so there's some unknown matrix X. Right, so instead of there being an unknown, yeah.
You wrote C dot X equals the trace of C dot X.
Yeah.
So like, the way I'm seeing it is C dot X is like an element-wise multiplication of the summation of across the entire matrix, but then the trace would just be the diagonal.
Yeah, but each entry of the diagonal is a row times a, it's a, you know what I'm saying? So each entry of the diagonal takes one row of each of those matrices here. Right? It takes one row of C and one column of one row of C transpose and one column of X, which is one column of C and one column of X, takes their dot product, and that's one entry of the diagonal. So any other questions? Yeah.
Because it's a linear operator.
Which one of many things? Yeah, it's just a shorthand for the same thing. They're all the same. Yeah, it's yeah. Just think of it as it's the linear operator on the space of PSD matrices, which is a linear operator. Any other questions? Okay. All right. So we're now thinking of this thing. It's so this will be a very non-obvious SDP, but let's do it anyway. So you have some unknown matrix X. You should think of it as just like in basis pursuit, there was some unknown vector beta, and you took a bunch of linear measurements of it. And here, there's an unknown matrix X, and you're going to take a bunch of linear measurements of it. So I'm going to observe Y1 and A1, Y2 and A2, and so on, where each Y is just going to be the trace of AI transpose X. So it's, yeah, maybe the easiest way to think about it is to think about something like the problem of matrix completion. So in matrix completion, you have some unknown matrix X, and I show you some of the entries. So I pick a random entry and I say, here's this one's 7, and this one's 17, and then I say, tell me what the rest of the matrix is. In those cases, each of these AIs you should think of as being a matrix with a whole bunch of zeros, and there's 1, 1 somewhere. That tells you which entry you're going to see, right? So if you think about that special case, you'll reduce this problem to matrix completion, but otherwise you can think of it as I'm taking some linear snapshot of the matrix, and I'm telling you what that value is. And I'm telling you that for a whole bunch of different linear snapshots. So matrix completion says, okay, given all these numbers, now I'd like you to fill in the rest of the matrix. There's many ways to fill in a matrix like that. So you say, okay, I want a completion that has low rank. right? So this is, you say, I want you to minimize the rank of X subject to a whole bunch of constraints that look like that. Okay, so this is, maybe you should imagine I'm saying the ij, the 1 entry is 1, the 1 7 entry is 2, and so on. I'm telling you a whole bunch of entries, and I'm saying now tell me what the lowest rank matrix is that completes this. And for exactly the same reason as before, this is a non-convex problem. So the natural relaxation is to again do this sort of L0 to L1 trick. So what does that mean? You think of, so what's the rank? It's just the sum of the singular values, the, I don't know, the number of non-zero singular values. And then you subject to all these constraints. So I want to minimize this thing subject to a bunch of constraints that say yi is the trace of. Okay, so now you can think of the natural relaxation, which is to replace this L0 norm by an L1 norm. So this is called, I mean, this is just, I'm going to minimize the sum of these sigma i's of X. So this is now the L1 norm on the singular values, whatever the dimension is. And then I keep dragging along these constraints. Turns out that this can be written as an SDP. This is some highly non-obvious fact, but this is called the trace norm of the matrix. This is also equal, when the matrix is PSD, it's equal to the trace of X. Right, so, and then you're trying to minimize the trace norm subject to a whole bunch of constraints, and it'll turn out that this thing can be written as a SDP, and proving this requires duality, so you'll see it sometime later on in the course. But for now, you should just take it as this is an example of a nice SDP. So this problem of matrix completion is you try to find the minimum rank completion. You can relax it and say, find me the minimum trace norm completion. That is, it matches on all the entries you observed, but has the lowest trace norm. And this is a convex problem. Turns out it's an SDP. Okay, so any questions about that one? Okay. I can't see that clock from here. Whew. Okay, where do I go? Okay, so I'll tell you what a conic program is, and then I'll leave everything else to Ryan. So there's actually some hard work that goes into proving that QPs are nested in SDPs, but he'll do that for you. Okay, so what's a conic program? It's one of those things where I thought really hard and couldn't think of a good example of a conic program that's not an SDP, but just take it as it is a generalization that one can write down. So what is the generalization? You think about saying, I want to minimize C transpose X subject to the constraints, some linear constraints on X. And the inequality constraints are phrased in terms of a cone. That is to say, I want that this matrix X should belong to some cone K. Right, so K is a convex cone. So this is called a conic program. You have a linear objective, linear constraints, but the constraint on the variable is that it should belong to some cone K. And now you can think about how do I get SDPs out of this. If I think of the cone K as being the cone of PSD matrices, then you'll recover SDPs. On the other hand, if you think of the cone K as being the positive orthant or the negative orthant, you'll get some LPs back. And LPs is when the cone K says Rn plus, like it's some orthant of the reals. Right? So you can think of this as some generalization of both LPs and SDPs, where you phrase the inequality constraints as rather than being either PSD or being greater than equal to 0 element-wise, you phrase it as X belongs to some convex cone K. Okay, so this is called a conic program. And I'm going to stop here.